right, let's get started. A few announcements first. So this evening I'll be releasing the grades for PS1. My goal is generally to get stuff graded by the Wednesday after you turn in, but as you recall, we had a sort of long grace period, so it took a while to get PS1 graded. There's still about 30 that aren't graded. I'm going to release the grades whether or not you lower the lights. Okay, you lean back on them. Well, I'll keep talking. So it's possible that some of you, when I release the grades, won't get a grade until it's actually graded. But I don't want to delay any longer. You've also received grades on labs. So if you see a mistake there, let the TAs who run your lab know. And finally, I think I did too good a job last time of encourage you to sign up for 30-minute appointments for help, as opposed to going to the CADE lab for help. Most of our help is scheduled into the CADE lab. On Wednesday and Thursday, we have multiple TAs there most of the day. So, unless the idea behind a 30-minute appointments is if you're pretty far behind in the course where you don't even know how to start the assignment. But otherwise, you can get help of the most trivial kind or deep kind of help from the TAs in the CADE lab. But to get it, you got to go there. So, how many of you have been to the CADE lab? Okay, so that's a minority of the class. It's easy to find. Here's where we are right now, Gardner Commons. MEB, which is the top, Merrill Engineering, that's where your labs are. And Webb is right next door, Warnock Engineering Building. So you're down, it's kind of numbered funnily. There's floors 1, 2, 3, and 4, but there's also floors L2 and L1, which are sort of the basement. So you're looking for level 2, L2, level L2, 224, 226. You go in there, you bring your laptop. If you don't have a laptop, you can use computers in there. Rather than go to the library and work on your assignment, go there and you can get TA help most any time. I really encourage you to take advantage of that. Okay. Any other questions or problems before we go? Proceed, brother. Okay, my lights are still dim. A couple of things I don't like about this room. One is the no power outlets. And the other is they put the light controls all the way in the back. Excuse me. Okay, so PS3 is out, and it's due Thursday like usual, and you're seeing now how the class rolls. All right, last time we started talking about loops, in particular while loops. So you'll eventually see that in Java there are while loops, and there are for loops, and there are for each loops. And we'll eventually talk about those other options. But the truth is, you can pick any of those kinds of loops and just keep one of them and throw the others out of the language. And that wouldn't stop you from doing anything you could do before. So the differences between those kinds of loops aren't important in terms of what kinds of programs you can run. Just some are more convenient at other times than others. So the while loop is the simplest one, and you can see it looks pretty simple. And that's why we started with while loop. Now, when I used to teach stuff like this, I would say, okay, here's a while loop. It's while followed by a Boolean expression in parentheses, followed by a list of statements. And what else would I have to explain? What else is there to know about while loops besides that it's got the keyword while, it's got a Boolean expression in parentheses, and it's got some statements? What would I need to tell someone if they're going to go off the program? Yeah?
I'm
Well, he said how not to create an infinite loop, but there's something more basic than that. That's certainly important. Suppose all you knew how to do was write syntactically correct while loops. What else do you need to know? Yeah? Okay, so the loop keeps on going until the Boolean expression is false. That's right. That's called the semantics, the meaning of a while loop. And you certainly have to know the semantics of a while loop to make use of it. And so the basic idea is when we're executing along, we hit a while loop, Java determines the value of the Boolean expression. If the value of the Boolean expression is true, or let me back up, if it's false, it skips to the end of the while loop and just proceeds with whatever follows it in the program. That's if the while loop wasn't there. On the other hand, if it's true, what does it do? What if this Boolean expression is true? Yeah?
Executes the statements and then goes back up and checks if it's true.
Right. It executes the statements, and then when it's finished, if it gets to the end of the loop, and I say if, because it could return from the middle of the loop or something, but assuming it gets to the end of the loop, it goes and reevaluates the expression. If it's still true, it does the statements again. Reevaluates the expression and so on until it becomes false. Now, if you want to avoid the loop running forever, what do these statements have to do? What's the role of the statements in preventing the loop from running forever? Yeah? Yeah, he said they have to update the values of the Boolean expression. They have to change something, you know, assign a value, do something that can eventually cause this expression to come false. Because you can't have a loop with an empty body, no statements at all, and that's truly an infinite loop, because there's never anything to change the expression to false. Okay, so I could leave it at that and say, okay, that's how it works. You figure out how to use them for these examples. Or we could even go over some examples. And here's the problem with that approach. It turns out that there are some patterns in the usage of while loops that come up again and again and again. You know, after you've written thousands and thousands and thousands of while loops like I have, you know, I can say, well, you know, 30% of the loops follow this pattern, and 25% follow this pattern, and so forth. I don't have anywhere near that exact figure, but I do know there are certain patterns that occur really frequently. So why not tell you about the patterns, show you what they look like, and that'll make it a lot easier for you to learn while loops. Because if you can figure out what type of loop is required, it's going to be a lot easier for you to code it. Because you can say, oh, I've seen this type of loop before. Now, I'm to the point in my life where I don't have to, generally, when I write a loop, I don't have to think about it very hard because I've written one like it before. But every now and then, I encounter a novel situation, and it makes me slow down and appreciate what a lot of you are going to be going through, which is figuring out how to use a while loop in a novel situation. But here for the next few weeks, I'm not going to give you any novel situations. I'm just going to give you loops, problems that you can solve using patterns. And the pattern we looked at last time was accumulation loop, and I want to go over that again. Now, this is what's sort of called the most vanilla kind of while loop. I call it an enumeration loop, which might be an unfortunate name because there's actually an enumeration class in Java, and it has nothing to do with it. This is sort of just the minimum amount of code you have to write if, say, you want to print out every number in a sequence. So you see, this method I've written here, it takes a starting point, a starting integer, and the number of integers we're supposed to use. So let's say the starting point is 10, we want to, and n is 4, then we're going to look at the numbers as we go through the loop, 10, 11, 12, 13. So it's very common that you need to do something to every integer in some interval. And it doesn't matter what you're going to do, I just put a comment here, do something with I. So the point of the enumeration loop is to be the basis of all the other types of loops. And that's just the general form that we saw last time. We have some counting variable, I in this case, very common to use as a counting variable. Int I equals start. And then as long as I is less than start plus n, as long as I has not gotten too big, we do something with I, and then we add 1 to I. So we're just sort of counting along. So if start is 10 and n is 4, I is going to go through the values 10, and then 11, and then 12, and then 13. But after it's 13 and we add 1 to it, we get 14, what's going to happen? Yep.
You'll check the Boolean expression again and see if it's false.
Right, I will be 14, start plus n will be 14, and 14 is not less than 14, so the loop ends. So we sort of count through the integers, do something to each one. That's an enumeration loop over integer intervals. Okay, now I'm about to look at other examples of enumeration loops, but let me see if you have any questions about this. Okay, we'll certainly build on this as we go forward. Okay? Then often what you want to do is iterate through a string. Do something to every character in a string. So what we do is we set our index to 0 right here. And we count I upwards until as long as I is less than the length of the string. When I is equal to the length of the string, the loop ends. So we basically generate, I goes through every possible index into the string. And inside the loop, we do something with the character at index I. And then we increment I. So that's sort of a minimum amount of code you need to zip through all the characters in a string. Now there are variations on themes. What if what you want to do is go through all the characters in a string in reverse order, from the last one to the first one, instead of from the first one to the last one? What would you need to change? Yeah?
Well, you could do a string length minus I.
Yes. We could do something like s.char at string length minus I, minus 1, I think.
Yeah.
But I had a different way in mind. That would certainly work. Yeah?
Set I equal to s length and switch the result to I.
Okay, so we said we can set I initially to s.length. We need to set it to s.length minus 1. We want to set it to the biggest valid index, so the s.length minus 1. Each time through the loop, we wouldn't add 1 to I, we would subtract 1. And we would, instead of saying while I is less than s.length, it would be while I is greater than or equal to 0. So once you learn these patterns, you know, it's not a big deal to adjust them to fit a different, a different requirement. What if we only wanted to look at the things at even indices? We want to look at the character 0, character 2, character 4. What would we need to change about this loop up here? Yeah?
Just do I plus 2.
Yeah, we say I equals I plus 2 there, so I equals I plus 1. Lots of variations on the theme. And this was the final kind of enumeration loop we looked at. It's how you consume a scanner. And here the code's particularly simple. We just say while there's a next token in the scanner, call s.next and do something with it. That call to s.next gives you the next token, but what else does it do?
Moves the scanner to the next.
Right, it changes the scanner. It makes the scanner, it gets the scanner closer to empty. It takes that token out of the scanner and gets you closer to the point where the scanner will become empty and the loop will end. So if you're not calling s.next inside the loop, you'll have an infinite loop. Now later on we'll look at arrays. We'll look at linked lists. We'll look at sets. All collections of things that you want to write loops to consume, and we'll adapt these patterns to those. But for now, we're just worried about looping over integer intervals, looping over strings, and looping over scanners. Okay? Now, on your current assignment, PS3, you need to write some methods that involve conditionals. If statements, but you also need to write loops, accumulation loops. So we're going to spend the first part of the day looking again at accumulation loops. So here is a prototypical accumulation loop, and I've highlighted in yellow how this differs from the enumeration loop. So if I go back to the enumeration loop, you can see it's a void method. It doesn't return anything, and there's not much going on inside the loop. If we go back here, so an accumulation method is going to iterate over an interval, just like the enumeration loop. But it's going to return something of some type, maybe an int, maybe a double, maybe a character. It just depends on the situation, maybe a string. And the white stuff is left over from the enumeration loop. The difference is we create a variable called ACC, or whatever you want. ACC stands for accumulation. Usually in a given situation, you can think of a better name. And It has the same type as the return type of the method. So if the method's supposed to calculate an int, your accumulation variable needs to be an int. And that's the variable in which you're going to accumulate everything. So if you're supposed to add up all the integers in the interval, that variable will hold the sum. If you're supposed to multiply them together, that variable will hold the sum. Typically, you initialize the accumulation variable to an identity value, like 0 if you're adding, or 1 if you're multiplying, or the empty string if you're appending strings. Okay? When the loop is done, well, it's all covered up there. Take a second to disappear. When the loop is done, you return the accumulation variable. So the whole point of the loop is to fill in the accumulation variable. And then, inside the loop, each time you get a new variable of I, you somehow combine A, C, C, and I. It just depends on what you're accumulating. You combine the loop variable and stuff you've accumulated so far. And that's an accumulation loop over integer intervals. So let's look away from this for a second and go find some code example. Okay? And there it is, that product method. So let's see, how does that fit the template of accumulation loop? So we're supposed to compute the product of the numbers of the n integers beginning with start. Okay? And we're going to return an int because we're computing a product. So what's going on right here? What about that previous slide tells us we need something like that? Yeah? Right, we need an accumulation variable. Might as well call it product because that's what we're accumulating. And we initialize it to 1 because we're going to multiply numbers into it. So we start with an identity element. And when we're all done, we're going to return product. That's straight out of the pattern that I gave you. So when you're writing an accumulation loop, you can just copy the last accumulation loop you wrote and adjust variable names and the types and so forth, but it's always going to follow the same pattern. Here's where you got to get creative. This is where you're actually doing the work of the method. And for each new I that I encounter, I say product equals product times I. So let's say start is 10 and n is 4. First time through the loop, we're going to be saying product is equal to product times 10, but product is currently 1, so product will be 10. What's going to happen the next time through the loop? What will product be set to? What do you think? Yeah. Be 10 times 11. The next number we hit is 11. So product will equal to 10 times 11, which is 110. So next time through, it'll be product equals 110 times 12, and so on. When we're all done, we've got the product in the variable. Now, what do you say to someone that looks at this and says, each time through the loop, it does the same thing? Each time through the loop, it is doing the exact same multiplication and the exact same addition. That's true on one level, but what's misleading about that claim? Yeah?
Because I changes every time you go through the loop.
Okay. Yes, you're adding 1 to I each time, but I is bigger this time than last time. And what about product? That changes too. And we've arranged it so that by the time we're done, product will have 10 times 11 times 12 times 13. We do one multiplication at a time through the loop. Right? Well, that's not going to work for me. Okay, so that is an accumulation loop on integer intervals. One that works on strings. So let me highlight the stuff that isn't part of it, that isn't specifically for the accumulation. We have a counting variable. We say while I is less than s.length. That's just from the basic enumeration. We, at the bottom of the loop, we add 1 to I plus 1. And we're done. What we've added is the accumulation variable, the accumulation operation, and the return. So what we're basically looping through the string, trying to accumulate the individual characters of the string into a reverse order version of the string. So we declare an accumulation variable right here. And it might not be obvious to you how you should initialize it, but I'm initializing it to the empty string. This takes no thought at all. You just return the value of the accumulation variable when you're done. And this is where the fun starts. Okay? I must have changed this last time in response to the question. Okay, so what's this going to do? What's it going to do with, let's say your string is Joe. First time through the loop. After one time through the loop, what's the value of R going to be? J. It will find J, it will append J to the empty string, and we'll get the string containing J. And then we increment I. So after one time through the loop, R is equal to J. Okay, next time through the loop, I is increased, so we look at the second letter in the second character in the string, and that's O. What will we do with O?
Put it in front of J.
You'll append it to the string R. You put in the character first, and so R will become OJ. Next time through the loop, E is your character, so you're going to stick it right there. And then there is no next time through the loop because we'll test it, I will be too big, and the loop will end and will return EOJ. So we accumulate the variables, we accumulate the characters in reverse order. Our starting point was the enumeration loop, then we just added some stuff to make it an accumulation loop. Okay, let's take this. Well, let's look at append ends right there. So we're supposed to take the return a string containing the n integers beginning with start, all appended together. So for example, suppose if start equals 5 and n equals 4, what do we want to return? We want to return a string. What do I want to have in that string when I'm all done? Yeah? Right, we want the string 5, 6, 7, 8. Okay? So we want the string to begin with start, and the next thing should be the number start plus 1, then start plus 2, then start plus 3. You know, if n were 1 and, if start was 1 and n was 100, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, now pretend this is on your assignment. What do? Do you do this? You say, okay, while, you've already gone wrong. What should you do?
Copy and paste.
Copy and paste, not from your neighbor, not from someone who took the class last year, but from yourself or from me. You say, have I ever written an accumulation loop before over string values? I mean, over integers. Right? This is doing accumulation over integers. You say, sure, I saw one in lecture. So hopefully you have all my code from lecture in your workspace. So we go copy the closest we have, which is that one. That's an accumulation loop that consumes string intervals. So we copy that. We paste it here. It's the closest thing we have. And then we got to start scratching our head and figuring out why this isn't quite right. So what do we need to change about this? And what can we leave the same? Yeah? One hand up. Yeah?
So your first declaration, you don't want an int, you want to return a string, you probably want to call it like sum or something.
Okay, so he's saying we're not, the thing we're producing by the accumulation is not an int, it's a string, right? We're producing a string containing digits. The method returns a string. It had better, down here, this accumulation variable had better be a string. So we better call the accumulation variable, make sure it's a string, because that's the kind of thing we're trying to compute. Now that's fine, but maybe product is not the right name for this. What would be a better name for the accumulation variable here?
Results.
Result. It's kind of generic. I do that a lot, though. try to be more descriptive. What is it we're producing in this string? What does it contain? Ints, yeah. Yeah?
Integer list.
It's an integer, it's a string. I'm going to call it numerals, just for the heck of it. Now, here's something you may not know. Hopefully this will work. It might not cause there's an error. If I want to change the name of a product, I got to change it here, and here, and here, and here, right? But if you go to the declaration, right-click, go to Refactor, and go to Rename, then you can type in the new value, which I said was the new name, which is numerals. Notice they're all changing. And you're done. Okay? So refactoring gives you a way of reorganizing your code in certain systematic ways. It sort of saves you a lot of editing steps. Yeah?
Will that change the other products earlier in the code?
He asked, will it change the other product? Say there's a variable product earlier in the code. Will it change them as well? And the answer is no, because refactoring knows about scopes.
Yeah.
That variable, what was products, was only visible between these two braces here. So it'll only change between the braces. Which means if you try to refactor and there's a brace missing, let's say you've got that kind of error, it probably is going to tell you can't refactor, because it's got to at least know where the scopes are. Okay, so we're producing and returning a string, so we're accumulating characters into a string. So where should what should numerals be to start with? Here's a way to think about it. Suppose there are no digits at all to accumulate. What should we return? Yeah? An empty string. Right? So usually what you put here is going to make, if n is 0, so you're supposed to accumulate no integers into a string. The only thing that makes sense to return is an empty string. So we're going to start with an empty string. So far, the only lines we've had to change have been the lines involving the accumulation variable. The bones of the loop stay the same. Okay? Now, this is going to have to change completely. What's the new value of numerals going to be? Let me put my glasses on so I can see the hands in the back. The hands in the back. What do we have to do with the current value of start? Yeah?
Numeral plus character at start.
Okay, you say, well, numerals equals numerals plus start.
No,
That works. You can append anything to a string, and it converts it to the right thing. Okay? So let's come up here. Let's print out the call. What did I call the method?
Append ints.
Append ints. And let's go from 1, and we'll do 5 on them. Okay? So I'm going to come, this is a subject of the lab tomorrow. You've seen me do this before. I'm going to set a breakpoint here. And then I'm going to run in debug mode. And what the heck? I guess I did the breakpoint. I didn't realize it. Okay, so it's at that breakpoint. So let's just execute that statement. So right now, numerals is the empty string. I is equal to start, so I will be 1. I is less than start plus n. So it's going to do numerals equals numerals plus start. So after this line of code, what's numerals going to contain? The string 1. And you probably can't see it, but oh, there you can see it. It kind of displays the string in a weird way without the quote marks, but the string 1. Now we're going to continue. I becomes 2 now. So if we look at I here, I is 2. It's still small enough. Now we take numerals, which is the string 1, and start, which is the number 1.
You don't want start.
And we append. And what do we get? 1, 1. And if we go another time through, what will we get? 1, 1, 1. And my answer, the reason I'm getting the wrong answer is I want to append I to the end of the string, not start. Now when we do this, we get the numbers glommed on in the right ones. 1, and then 2, and then 3, and then 4, and then 5. And then the loop ends and we're done. So easy to make mistakes. I've written thousands of loops. I didn't make that mistake on purpose. So don't feel bad when you make mistakes. Okay? Any questions I could answer about that? It's the kind of thing you'll be doing on the next assignment. Yeah?
How come if I hover my mouse over my loop variables, it doesn't show the same info as yours does?
Okay, so she's asking how come she hovers the mouse, it doesn't show the same info. Well, it will not show the info if you're just sitting here. Only when you're running it, and only if you're running in debug mode.
How do you run debug mode?
Well, debug mode, there's a little bug icon right up there at the top, which you won't be able to see from my projector. You run it right there. But you often have to set a breakpoint so it'll actually stop in the middle of executing. And like I said, that's the subject of the lab tomorrow, to learn how to use a debugger, because it becomes very useful when you're debugging loops, that you can step through and watch what's happening. Okay? Some people are in the habit of putting print statements in so they can trace what's happening with their loop. And that's fine in some circumstances, but it's better to know 2 tools than just one. So I encourage you to learn to use a debugger. Okay. Well, what about this loop here? Returns a string. It's supposed to take a string and return just the lowercase letters. Just basically gets rid of the things that aren't lowercase letters. So that's an accumulation loop. We're taking a string and accumulating a different string. So where should we look for inspiration? Yeah?
One of your accumulation loops that deals with strings.
Right. So here we have, he said, an accumulation loop that deals with strings. So here we are. I'll just copy that as my starting point. We'll come down here to all lowercase and paste it in. I think I pasted it in the wrong place. And there we go. Well, let's see what we have to change about this. The loop we copied from was returning a string, and so we actually got this type right. Maybe we could think of a better name than R. Not my best variable name ever. It's good if the accumulation loop describes what it contains. So if we were going to refactor this, what should we call it?
Lowercase string.
He said lowercase string. That seems a little long to me. There's a balance between descriptive and too long. I'll just call it lowers, whatever. All right. So everything else is good. We just got to change. This is the heart of the matter. This is where we have to actually do something different from every other accumulation loop. So what is it we want to do here? Remember, we're looking at this character. I gives us the one to look at. So what should we do with character I? Should we append it to the string we're building? Should we ignore it? Something in between? Yeah? Okay, we don't want to append it to the beginning, he's saying, because we're not trying to do a reverse now. We're trying to just filter out things that aren't lowercase letters. Is that what we want to do? Someone else tell me that. Is that what we want to do? Just append the character to the end of the string we're building. Why does that not seem right? Yeah?
We need to make sure that the letter that we're appending is a lowercase.
Right. We better not do the append unless the character we're appending is lowercase. What would this do? What would this method do if we just left it alone?
Return exactly the string.
Right. It's just making a copy of the input string. It's taking every character and appending it to the end of a new string. So we get back the same thing we started with. We only want to append lowercase letters. So how can we make it so that this statement is only executed if this character is a lowercase letter? Yeah. Need to use a conditional. There's no rule against putting a conditional inside a loop. So we need to say this. If something is true, then do the append. Otherwise, ignore the thing altogether. Only question is, what has to be true? What needs to be true before you do the append? Yeah?
The character has to be lowercase.
The character has to be lowercase. And fortunately, there is a character class. And there's an is lowercase method. And what are we testing for lowercaseness? S.charAt. Boom. So now we're saying, if the character, if s.charAt is lowercase, then append it to the string we're building. Otherwise, ignore it. And we just go through the string, doing that to everyone we encounter. So what if there are no lowercase letters? What do we get back?
An empty string.
An empty string. If this conditional is never, if this conditional here is never true, this will never be executed, and lowers will never change. We'll return the empty string. What happens if every character is a lowercase letter? Then we'll return the same string. Every character will be included, and there'll be an in-between case where some of them are lowercase letters and some aren't. Now, I imagine that a number of you are wondering, how can your classmates look at that and figure out what it does? What is the trick for looking at a while loop and figuring out what it does? Think back to the day that I talked about Beethoven's Ninth Symphony. If you just look at the score, it's pretty hard to understand what it does. What do you have to do to understand? Yeah?
Just read it through one line at a time.
You said read it through one line at a time, but it's actually a little more, I think literally what you said is quite right. What do you have to do besides read each line one at a time?
One expression at a time.
No, well, okay. Yeah. Well, he said practice it. With the symphony, the answer would be play it. What corresponds to play? Yeah. Well, you can certainly add comments. The act of adding comments adds to your understanding, yeah? Right, you run it in your head one line at a time, right? So it's not like we only look at that first line once. But you might think what this does many times. So if you're trying to understand a loop, just pick an input string and just simulate the program in your head if you want to understand how it works. Eventually you get to the point where you look at this and say, oh yeah, okay, I got it. It takes a little longer than that. But until you've written and read lots and lots of loops, it doesn't come fast at all. You need to be able to just say, okay, it does this, and then it does this, and then it does that test, and keep track of the values of variables on paper. That's true, so it executes this. That's false, so it does this. Then we're back up here, and so on. Right? Just like most of us can't predict what a musical score is going to sound like without just playing it. Most of us can't predict what a program's going to do without running it, either in the debugger with breakpoints or in your head with paper and pencil. Okay? This is a prototypical accumulation loop on scanners. And remember, the enumeration loop just involved while scan.hasNext, do something with scan.next. So turn accumulation loop, we declare the accumulation variable, we return the value at the end, and we update the accumulation variable inside the loop. So here, with total length, let me show you an example of here. Take this for example. We have the token A, the token BC, the token DEF, the token GH, the token I. Their total length is 1, plus 2 is 3, 6, 9. The total length is 9. I want to add up the length of all the tokens, ignoring the white space. So what I do is, initially, my accumulation variable is going to hold the total length of all the tokens I've seen so far. So initially, I haven't seen any tokens, so it's 0. Each time we see the token, we take length and we add to it the length of the next token. That's the new value of length. When we're all done, we return it. Okay? I've got one down here, a different method on the scanner, that assumes that all the tokens are int tokens and adds them all up. Okay? So I've copied the closest solution I have in the past, and there it is. And now I've just got to figure out how to add them all up. Well, what should we call the accumulation variable?
Sum.
Okay, sum is good. Something that might be more descriptive and might help you is to call it sum so far. The sum of all the tokens you've seen so far. Okay? When we're done, we're going to return the sum, and the only thing that remains is, how do we update the sum? If you have the sum of all the tokens you've seen so far, and you've just seen another one, yeah?
Will you integer parse int?
Well, it turns out we don't have to parse an int. What can we do? Yeah? Right, there's a method called nextInt that does the parsing for you. And really, instead of saying has next, probably be a little cleaner to say has nextInt. So that just goes through pulling ints out of the scanner, add them all up. Now, if it hits a token that's not a scanner, you're going to get an exception. It's going to say no such element exception. We're assuming that the only tokens are ints. Okay? So what we've done this time and last time is we've seen the pattern of accumulation loops. We run set of examples from scratch, and then we copied those down and modified them to be new solutions. And that's how I recommend you do this until you get to the point where it's faster just to type the thing from scratch than to go searching and copying something. Because you'll eventually get to that point. All right, let's take a break and we'll look at a different form of loop. All right, let's get started again. Okay, so now we're going to talk about a second kind of pattern that I see a lot, and it's called a searching loop. And here is how, this is what a searching loop looks like on an integer interval. So again, the white stuff comes from the underlying enumeration loop we're building on. And the yellow stuff is what we have today. So in a searching loop, you're searching for some element, an integer in an interval, a character in a string, a token in a scanner, that has some property. And as soon as you find one, you return it. There may be others with that have that same property, but we don't care. As soon as we find one, we return it. And so the way it looks is it's just an enumeration loop, but inside, get the pointer here. Inside is a conditional, and the condition says in this case, if the integer that you're looking at right now satisfies a property, return it. So what happens to the loop? You find the thing you're looking for, you return it. The loop ends, the method ends, everything ends. Whoever called the method gets the answer back. Okay? So that's the hallmark of a searching loop. You return from inside the loop as soon as you recognize you found what you're looking for. What does it mean if the loop ends? What if we fall off the bottom of the loop?
I never satisfied the property.
It means you did not find anything that has the property. But you have to return something because the method says you return at the end. So typically, the specification will specify, will say, if you don't find the integer you're looking for, return -1. Return negative infinity, something. There'll be some sentinel value that says, I didn't find what I was looking for. And, what you do, it may depend on, if you're only looking at positive integers, then returning -1 makes sense. So it's going to depend on the specification of the method. It has to be some way that you agree with the user how to indicate. Okay? So that's our pattern, an enumeration loop, and inside it, we have a conditional that has a return involved. Or if we end the loop, we return some value that indicates failure. So before we look at the other patterns, let's go look at an example in code. Okay, so searching loops. Here's my first one. We're given a string and we're looking for a character that is a digit. If we find it, we return it. Otherwise, if we don't find it, it says to return the underscore character to indicate I didn't find a digit. Okay? So where do we go for inspiration for this? It's our first counting loop, our first searching loop. What would make sense to start with? It's a searching loop, but it involves, no, I'm skipping that, never mind. We didn't talk about strings yet. Let's look at this one. Looking for a number between 1 and n that has a cosine greater than 0.99. Or 0 if there's no such n. Okay. So, where do we go for inspiration for this? What do you think? Where have we done something that's similar to this? Right. So the base loop is an enumeration loop. So let's go copy an enumeration loop from last lecture on ints. So this is the base of an enumeration loop. So that's good. We will now go to the searching loop here, and we will paste this in its place. Now immediately we have a problem because there is not a start, before we had start and end, this one just gives in. So how are we going to fix this? What should be the initial value of num?
1.
Yeah, it says you start with 1, And then while num is less than n plus 1. So basically 1 is playing the role of start. Now you might look at that and say, that's one way to write it. What would be another way to write that inequality? Num is less than n plus 1. That looks complicated.
Num is less than or equal to.
Yeah, we could say num is less than or equal to n. That amounts to the same thing. A little more succinct looking. And we don't want to print anything out. Okay, so there's our enumeration loop that does its thing. And we just got to add two things. We got to put that conditional part inside the loop, and we got to give a return at the bottom. Well, let's say the loop ends. What do we put here? It says return 0 if there's no such integer. Because we know it always starts with 1 and goes up. I guess I should say n must be positive. So we return 0 for failure. Then what's left is to put a conditional here that if we found what we're looking for, what do we do with it? Return it. So if num is what we're looking for, we return it. And the thing to realize is you can get that far with a searching loop without having to deal with the thing, the property at all. The specification tells you what to return if you fall through the loop. And you know what to do inside the conditional. You return the num. Yeah?
They're all going to be a sub-loop with an if statement.
Right, they're going to be a loop with an if statement. But furthermore, the if statement, the body of the if statement will be a return statement. Right? That's what gives it away. So we just have to figure out, is our number the one we were looking for? How do you do that? What has to be true? Right, we'll take the cosine of the number and ask, is that greater than 0.99? And if it is, we'll return the number. Otherwise, we'll keep looking. So as soon as it finds a number with a big enough cosine, we return the number. We stop looking, return the number, ends the loop, ends the method. Life goes on. If we never find one, we'll follow through and return 0. So if we, let's see what I've got up here. I've got a main method that's going to call find in. So, okay, so here we are, and I'm not even going to look at the values. I just want you to watch what it executes. We do the test, we do that test, wasn't big enough. We look at a bigger number. We do the test, wasn't big enough. We do the test, wasn't big enough. We do the test, we were done. So it must have, what happened there was it was, I don't know why it returned. It was supposed to go up to 100. I screwed something up. But this is sort of like watching the score play when we looked at Beethoven's symphony. By setting breakpoints, you can watch the, you can watch control though. I'll try again and see what I did wrong. Something seems a bit screwy today. Oh, I know what happened. My finger slipped. I clicked the wrong thing. So it's just looking. Hasn't found it yet. This is what you've got to be able to. See, if you were doing this by hand with a calculator, you would have gotten completely bored by now and given up. Because you got to keep looking. And I may get completely bored and give up. How will you know when it's found something? That return statement will be highlighted. I should have known the answer before I started this. Here we go. So it found the answer, and it is 25. Okay? That pattern you just saw is the kind of thing you got to be able to visualize in your head to understand it. And learning about the debugger will help with that. Okay. So that's an example of a loop, a searching loop involving ints. Before we go on, let's look at a different one. Well, I'm not liking these examples. We'll do something else first. Let's go back to the searching loop. That was a prototypical searching loop involving integer intervals. Right? Here's one involving strings. And again, the white stuff is common to enumeration loops, accumulation loops, searching loops, optimization loops. It's just the minimum scaffolding that's needed to get things going. And again, what you add is a conditional that returns if satisfied, and the value that indicates failure. So if you start from an enumeration loop, you just paste in the yellow stuff, and you're good. Okay? And the stuff you're adding is the same stuff you added to the other, to the integer interval. So the pattern is strong. Oh, let's go back and do it. So I'm given a string. Maybe the string contains AX3ZQ. I'm trying to find a digit. That one contains the digit 3. So if it finds the 3 character, it returns it. Otherwise, it keeps looking. And if it doesn't find it, it returns underscore. So we need inspiration. What's our inspiration going to be? Yeah?
The lowercase one? We were like searching through a string for lowercase.
Well, there was the lowercase one, but that was an accumulation loop. We could start. Why not? Let's start with an accumulation loop, and you suggested this one here. I was going to say start with an enumeration loop and add, but we can start with an accumulation loop and subtract to begin with. So we're going to take out the stuff that is just because it was an accumulation loop. This was just because it was an accumulation loop. And this is just because it's an accumulation loop. Okay, and what's left is the enumeration loop, pretty much. The basic of any loop you write over strings is going to look pretty much like that. Okay, now we've got to turn it into a searching loop. So I like to start with the bottom. What do we do if the loop ends? Meaning we did not find a digit. What are we supposed to return? Right. You know, that's not something that that is automatic. It just depends what the spec says. It said return underscores. Nothing special about underscore, except that it's not a digit. So there we go. What else do we have to do? What do you have to add to the enumeration loop to turn this into a searching loop? Right, you need a conditional that tests. If I have found what I'm looking for, return it. Okay? So that's easy. If I have found what I'm looking for, return it. In this case, what is it? Right, the character at index I. Boom. All right, and then I've just got to ask. I've got to ask the question, is what I'm looking at a digit? And it helps to know that the character class has a whole bunch of handy methods like is digit. And that's all that's required. So if you understand that, you start from the, you use the pattern. And the only two things you have to figure out are the conditional inside the loop. Really, all you have to figure out is the condition that controls the conditional inside the loop and the return statement. They suddenly aren't so daunting anymore, as long as you know where to go for examples. And there are going to be plenty of examples online here after lecture. Are there any questions I could answer about any of these two that I've just done? Yeah?
So, like, where does it specifically start the digits inside of this?
Right, say that again.
Where does it specifically look for, like, the digits inside of the method?
Okay. So we've got, he said, where does it look for the digits? And we got the string, so we're looking at every character of the string in turn. So each time through the loop, we have a different value of I. I counts up 0, 1, 2, 3, 4, and so on. It's right here. that tests character I. So first time it tests character 0. If that's a digit, it returns character 0. Next time through, it'll be testing character 1, returning it if it's a digit, and so on. Any other questions? Yeah?
We don't really require the brackets for the if statement, right?
You're saying you don't need these?
Yeah, because it's only a single statement.
Yes. Java is perfectly happy if you write if statements with a single statement that way. Joe is not happy if you do that. I would worry more about what makes Joe happy than what makes Java happy. You're right, you can write your code in fewer lines if you leave out braces sometimes. But yeah, I consider it bad programming style, especially for beginners. Yeah.
What's your preference if we put I++ instead of I equals I+1?
Okay, so there are lots of shortcuts. He just asked a question about something called I++. And usually you have to ask that question in class about a dozen times before I give in and let you use it. So you've got 11 to go. Try to keep things simple as possible for as long as possible. Don't worry about what he asked if you don't understand what I said, because I don't want you to understand what he said. I like to keep some things buried. Let me tell you what can go wrong if you don't use braces, like if you write it like this. So you might say, oh, okay, I need to add another statement to my if. And before I do this, I need to say I equals I times 2 for some reason. And then do the return. I equals I times 2. Okay, now in this case, Eclipse is giving an error because of this return statement. The return statement can't be followed by another statement. So in Python, there are no braces. You rely totally on indentation to communicate which statements are inside the if and which are not. In Java, that's not the case. So even though you've indented it like this, in Java's reading it like that. So since the indentation can fool you, if you're not careful, I prefer to use the things that really matter, which are the braces, even when they're not strictly required. Any other questions? Okay, we'll go look at the last example of a searching loop. That's in the wrong place. And that's a searching loop on scanners. So again, the white stuff is from enumeration loops. Again, all we have to add is the if that says, have we found the token we're looking for? If so, return it. And then something at the end that returns that indicates failure. So same, here's the previous one, here's the one before that. The yellow stuff is the same. The white stuff we inherit from other kinds of loops. So back to this. This says, if the scanner contains a token of the desired length, returns it. Otherwise, returns the empty string. Okay? So where can we go for a starting point? Since I haven't written a searching loop yet. Maybe we'll go look for an enumeration loop. Here we are. So that's our starting point for and we need to add to it. Well, we're not going to be printing anything out, so I'll take that out. What's gone wrong so far? Why have I got a red underline here? SC.
You don't have a scanner declared? Or
well, we do have a scanner. We're getting a scanner to look for, but it's got a different name, so I need to be sure I use a consistent name. Now, what do we do if that loop happens to end? It says return the empty string to indicate failure. That's easy enough. And then in here, if, okay, so if we found the token that we were looking for, we need to return it, right? Tokens, next. Now I just made a mistake, and I'm sure that many of you noticed it, but let me play on a little bit longer. What do we have to put in the parentheses here? How do we know if the current token is the one we're looking for? Is A one we're looking for? Yeah.
If tokens.next.length equals desired length.
Right. So we get the next token, we check its length, and if it's equal to the desired length, we
Can't do dot length on has next.
oh, that was not a deliberate mistake. So tokens.next.length. So we get the next token, and if it has the desired length, we return it. So there's a very serious error in here. I've got two people that are willing to point it out, but I'll let you point it out. Say a little louder. No, the return statement in the while is fine. Yeah, we'll see that in searching loops, yeah.
You call the next length, but then when you return it, it's going to call the next one.
Right. Notice what's happened here. I got the next token right there and checked its length. But I don't return that token. I return the one after it. Every time I call tokens.next, I get a different token out. So the one I'm testing is not the one I'm returning. Okay? Now, you may say, we did the same thing up here. You tested s.char@I, and if it had the right property, you returned s.char@I. Up here, I tested num. If it had the right property, I returned num. So why are these two okay, but that one down there isn't? Why is, in particular, why is this one okay? Why is it okay to test s.char@I and then return s.char@I? Yeah?
Because I hasn't changed yet.
Because I and s, for that matter, have not changed yet. So I'm going to get the same character both times I call it. I doesn't change. Up here, num doesn't change between here and there. It's about to change there, but between here and there it has the same value. But down here, this call to tokens.next changes what? Besides getting the next token, what does it also do?
It's changing your scanner.
It changes the scanner. It pulls a token out so that the next time you ask tokens.next, you get a different answer. Yeah.
So to solve this, could you put a string variable before your if statement in the while loop and assign it with the value of the next?
Right. So the idea is, when you're working with scanners, you got to be careful. So what we'll do is we'll call tokens.next here and save the answer. Then we will test. Now we've got the next tokens. We'll test it there, and if it passes muster, we'll return it. So we avoid calling tokens.next twice in the same iteration. So that's something that, it's a very subtle error, but you would notice it right away if you ran it. Yeah?
Is it okay to define a variable inside a loop like that? Like, should
Okay.
we technically define it above the loop?
He asked, is it okay to define it in a loop like that? As a general rule, when you declare a local variable, it's better to declare it in the smallest scope possible.
Okay.
So the only place we need this variable is inside the loop. So we declare it inside the loop. Now, another thing I've noticed, so what he was saying is, could we not have declared it out here? I could have done this. I could have said string token, and then right here said token equals tokens.next. And that works. But token is only of interest inside the loop, so I say declare it in the loop. Nothing wrong with that. Now, a number of you, I've looked at a lot of student code, and for a lot of you, at some point told you to declare all your local variables at the beginning of the method.
Yeah.
Don't do that. Declare them when you need them. Right? If you declare them up here and initialize them down here, I've got to look in two places to figure out what's going on. I'd rather you declare and initialize it in the same spot. It's someone's idea of good programming style, but it's not mine. So don't have a block of declarations at the top of each method of all the variables you're going to use. Declare them where you need them, such as right there. I don't know if there are any other examples to work on. This one, I needed it, so I declared it right away. Okay? Any other questions about this? Where were we? This one here. Well, let's try this one. Return the number of positive integers that are factors of n. Is that a searching loop? What kind of loop is that? Yep.
Accumulation.
He says accumulation. What do you think?
Both.
He says both. What's different about it from a searching loop? Yeah. He says there are multiple answers. Yeah, what I would say is it's not really like a searching loop because a searching loop is never a return inside the loop. This one can't. You have to look at all the elements. So I call this an accumulation loop with a twist. The twist being what? What will the accumulation loop contain? Yeah.
You're searching for something specific?
Well, we did an example like this before. It's an accumulation loop where we do a conditional test before we do the accumulation. So let's see how that would work. Let's see what we have up here. I'll start with this one. So this was an accumulation loop. So let's come down here. And let's try to use that accumulation pattern here. So we got to count through the integers basically from 1 to n and count how many of them are factors of n. Okay? So we need to start with something. So let's, I'm just going to call this variable I. Okay? Now, for how long should this loop iterate? Yeah, we got to look at, basically we got to look at every number from 1 to n and decide whether or not it is a factor of n. So I need to say while I is less than or equal to n. Okay, and then, okay. So basically what we've done is we've gone back to an enumeration loop. So to turn to accumulation loop, what do we need to add to it? Yeah?
Save on runtime, can you do n over 2? I is less than or equal to.
Yeah, but you got to be careful about n though. He's asking couldn't we go up to n divided by 2, but we got to count n as well. N is a factor of n. So make this accumulation loop, what do you need?
Accumulation variable.
You need an accumulation variable that's going to count the number of divisors it finds. What should we call it? Yeah, count's a good favorite of mine, so we will count 0. We'll start count out at 0. When we're all done, we're going to return count, because that's the way accumulation loop. So far, this looks just like an accumulation loop. And then we're going to look at each integer in turn, and we're only going to count it if it's of interest. So it's sort of like a searching loop in that fashion. There's got to be a test in here that says if the number is of interest. But the difference is, if it is of interest, you don't return. What do we do if we discover I is a factor of n? Yeah, you say count equals count plus 1. We increment the count. Now, how do we decide that I is of interest? How do we know that I is a factor of n? Yeah?
It's the number of modules. If it's 0.
Okay. So we say if n modulus I equals 0. It just means if I evenly divides n. So I say it's an accumulation loop with a twist. The twist being you don't do that unconditionally. You only do that for some numbers. And it's not like a searching loop because a searching loop would return right there. So if I'd ask you, return the first integer that is a factor of n, that would be a pure searching loop. So there are always these little adjustments that you need to make to make things work. Now, on your assignment on PS3, it begins with, I don't know, 2 or 3 methods that involve just conditionals, no loops. The rest of them involve accumulation loops, and it says it right in the hints. There are hints in the comments, and all the hints say use an accumulation loop. So that's a big clue. I've given you lots of examples here to start with. I've given you examples of accumulation loops involving integers, involving strings, involving scanners. Accumulation loop with the twist that we only count some, we only process the elements some of the time. So for any problem that you have to solve, there ought to be an example that you can pull up with the Canvas Project Manager. That's a good starting point. Okay? TAs will not be impressed if you call them over with a completely blank thing. At least paste in the starting point. And now, I realize having said that, I don't want you to be afraid of the TAs. They're not going to get mad at you. What they'll do is say, find a starting point and paste it in. Okay? And remember, this is worth showing you. It's my last thing here. Here we are. If I go to the home page, and I click Help, right over here, staff drop-in consulting schedule, those are all the times when the TA is available. Look at Thursday, it's just packed full. Wednesday, lots of times. You click right here to put yourself on the TA call queue, and they'll find you, as long as you're in the lab. Okay? All right, I'll see you next time.